going to pick up the best and going to have the maximum amount of growth, and that will bring in a lot of stress on our resources. So I think the right way to do it is, as what you are presenting today probably, is on the use of these analytical tools that will help us to predict performances of HVAC systems, and then be better equipped to handle the energy consumptions, yet not compromise on the basic requirements.
Yeah, no, well said. You're absolutely right. So we're just about ready to start. It looks like.
Yeah, I think we should. We are just about 2 minutes away from to 7:30. So maybe that uh, I'll hand this over to Tapas ji to and Suhas ji, if you have joined, Suhas Mathur ji, you can.
Yeah, I have.
Yes,
yeah,
sir.
Yeah.
Just we have now we are live in YouTube as well and all set. Just about to go for 2 minutes only. We'll start at 7 o'clock. 7:30. 7:30. Yeah.
So I have 7:58 here, so it's what is it, 11 and a half hours or 12 and a half hours difference, I guess. It's what time is it there? You have.
It's 7:28 p.m. I think it's 11 and a half.
Okay, yeah. What other lectures have you had this year? Have you had Stephanie Taylor?
We have had Stephanie Taylor as part of a national program. She presented as part of a panel with other members of the task force, epidemic task force. And then for this Delhi chapter of ASHRAE, we'll have another program on net zero carbon concept on 16th. By Luke Leung, and then we have Drew Crawley presenting on weather on a weather-related topic. It's a new thing he will be presenting, and then we have Mr. Mark McCracken from CalMac. So these are the few programs we have lined up. We just want to be close to the theme of carbon neutrality or energy efficiency or resilience.
Yeah, those were all good speakers, and I'm sure then you've had Bill Blomfleff on as well then, Professor Blomfleff?
Yes, he also came as part of that panel on specific to the coronavirus that was held at a national level, along with Kishore Kankari.
Okay, yeah.
Yes.
Kishore's an interesting man. He's a smart guy. Oh.
Yes, he has been also associated with the ASHRAE India chapter, doing some programs in the last many years.
Yeah, I have a lot of respect for his capabilities.
Now it's 7:30, sir. Should we go ahead?
Yes, we can start playing the video. Yeah.
We, the Indian Society of Heating, Refrigerating and Air Conditioning Engineers, ASHRAE, stand tall in the Indian industry with over 10,000 professionals as members and almost an equal number of student members. Founded in 1981 and headquartered in Delhi, we operate from chapters and sub-chapters spread all over India, bringing our entire industry together. Individuals become members of our society according to their professional and academic standings. Our roadmap of the future looks very bright, with thousands of new members joining this technical society every year and bringing in a fresh outlook to our industry intelligence. ASHRAE disseminates knowledge through its technical committees, which consists of some of the best minds of our industry. It publishes technical books, newsletters, and a prestigious journal, distributing the wealth of knowledge to all its members. Working with government departments, ASHRAE helps formalize industry codes and standards. ASHRAE promotes research by offering financial support to student members to carry out groundbreaking work in technology, systems, and processes. Our educational wing, ASHRAE Institute of Excellence, organizes training programs and workshops to help members enhance their skill sets. Our specially designed certification programs under ICP, that is, ASHRAE Certified Professional, empower professionals to always be in step with the prevailing technology. Specially designed courses for technicians are offered to meet the ever-increasing demand for a skilled workforce. ASHRAE organizes exhibitions, conferences, panel discussions, and product presentations throughout the country. We organize the industry's largest international exposition in South Asia, ACREX India, to showcase the cutting-edge technology, innovation, and provide a platform for closer interactions amongst the decision makers in the industry. The ACREX exhibition is now growing from HVAC&R show into BFA, Build Fair Alliance. This brings together several allied shows connected with the building services industry, all at one location. Our chapters organize several other popular events like ACREConf in Delhi, Raycon in Kolkata, Symposia in Mumbai, TechFest in Goa, and many more. We are committed to provide training and career guidance to our student members through seminars, lectures, quiz contests, and site visits. A-Quest, a prestigious quiz competition organized by ASHRAE to catalyze the transformation of the budding engineering professionals. ASHRAE provides a platform to potential employers to select student members for careers in HVAC and our industry at the ASHRAE Job Junction. Young minds are made aware of the need for saving power, clean air, and sustainability. The K-12 initiative of ASHRAE focuses attention on school students' development to inculcate a scientific fervor and help develop them into responsible citizens. Speedy information is imperative to keep moving forward in this hyper-connected digital age. Searcher, a specifically designed search engine, is now available, which allows access to a well-catalogued database on HVACR and building services industry with just a few clicks. ASHRAE cooperates with various national and international bodies, industry, governments, academia, think tanks to promote the concept of sustainability, environmental protection, and energy efficiency and conservation, to enter and explore the universe of the Indian HVACR industry. Log on to ASHRAE.in that unfolds a panorama of information. Let us engineer a sustainable future together through ASHRAE.
Yeah, thank you everyone. Just before opening the program, just want to showcase few slides of LP Euroflex, the gold partner of Delhi chapter of ASHRAE for the society here. They're into the insulation solution. They have a portfolio of over 10,000 products, founded in 1985. Few brief about LP Euroflex, you can see over here. Key certifications, key projects, what they have done in airports, hospitals, IT sector, industries, government education institutions, and prestigious international projects they have done. These are the product line of LP Reflex. Contact number is displaying over here. You can contact him regarding the insulation solution. So, thank you everybody for joining this program. And time has come today. This is the first topic under the international speaker series. Yes, this program is organized by Delhi chapter of ASHRAE, supported by IGBC, CII, ASSOCHAM, GEM, ASHRAE India chapter, ASHRAE Chandigarh chapter, Prem Jain Memorial Trust, RAS Vadodara chapter, Rotary Vadodara Greens, and of course, supported by annual partners as well. Gold partner LP Reflex, annual partners Standard Refrigeration, Advanced Valves, Fluke, Lloyd Insulation, and membership partner Aircon Engineers. So yes, we are going to cover today using thermal comfort tools to evaluate discomfort possibilities due to enclosure design and choice in HVAC system. So without delay, further I request Program Chair of Delhi Chapter of ASHRAE, Mr. Suhas Mathur, to proceed from here. Thank you. Thank you very much. Over to you, sir.
Thank you, Tapas, and welcome everyone to this international speaker series at the Delhi chapter of ASHRAE. We have today Mr. Robert Bean, who is joining us from Alberta in Calgary, Canada, and he is the director of Healthy Heating and the co-founder of Indoor Climate Consultants. He is a retired engineering technology professional, and he specialized in the design of indoor environments and high-performance building systems. He has been the ASHRAE Distinguished Lecturer, recipient of the Lou Fieg Award, Distinguished Service Award, and an instructor for the ASHRAE Learning Institute. He has authored several papers, articles, and course curriculums, and serves on numerous technical committees related to indoor environmental quality, building, and energy systems. His motto has been to design for people, and good buildings would follow. So we hope that you will enjoy this session and learn from his experience. If you have any questions, then please type them in the question and answer tab, and we will either take them as the session goes along, if if the speaker is comfortable, or at the end of the session. So I would now like to hand it over to our speaker, Mr. Robert Bean. Over to you, sir.
Thank you very much. It's a pleasure being able to share the knowledge that I have with your membership this morning here, this evening for you. And maybe what we could do is get into the slides. Are you able to see my slide? First slide?
Not yet. You will have to share your screen.
Let's see. I think there we go. You can see it now.
No.
Let's see how we can do this. Make sure we maybe I can see it on mine, but maybe can you let me have control over the slides?
Yes. Tapas, can you check if the controls are appropriate?
Let's see, share screen.
Yes,
So
I think.
now?
Yeah, now it is visible. Please go ahead.
Very good. Okay, thank you very much. So today we're talking about, and the standard disclaimer there, so I'm not prepared to read that today, but just basically you should know that I'm here as a guest, and my views are my views, but the information is based on scientific principles, fundamentals that are within the handbooks, engineering handbooks, and it is purely just to talk about thermal comfort and the tools that are available to engineers to assess the indoor environment from a thermal perspective. So that's what today's presentation is all about. So there's the title and what we're going to talk about now. This is actually part 3, really. For those that maybe haven't studied parts 1 and part 2 of the course that we teach, really it was about human physiology and how people sense and perceive the indoor environment thermally, and then the contents of ASHRAE Standard 55. So I will present today the actual application of that knowledge for the purposes of using the tools to assess the indoor environment thermally. For those that maybe you've skipped steps 1 and 2, I'll try to address those as we move through the presentation, but we'll certainly answer any questions. And I think just for the sake of moving along, we'll answer questions towards the end of the presentation. So if you have questions, just put them aside or put them in the chat and we'll address them at the end. Certainly when we look at design anywhere in the world, really, we have engineers and architects that have to be in compliance with whatever the local codes are. And there usually is some reference that to be in compliance with the building codes that we have to maintain some sort of indoor temperature condition. And oftentimes that temperature condition is referring to the dry bulb temperature. That is whatever the thermostat is reading. And 99.99% of all thermostats only measure the dry bulb temperature or the air temperature. And that if you meet those requirements, that you typically are in compliance with the building codes. But as those of us that have studied human physiology and the contents of ASHRAE Standard 55, we understand that air temperature is a very poor proxy for what people sense and perceive when it comes to thermal comfort. And that in fact, there are many other metrics that we need to pay attention to in order to design architecturally good buildings, including the enclosure design itself, which is also addresses fenestration, window to wall ratios, reducing thermal bridging, all of these types of things come into play. And that when you look at what people sense, not what the building code provides, but what people sense, it really is this. And this might look like there's a lot of things going on here, but the reality is that each and every one of us, when we sit in a room, we experience the dynamics and the transmission and the transient nature of the environment. And so when we think about radiant energy from the sun, shortwave radiation hitting the building, and then either coming through our glazing systems as shortwave radiation, and then being absorbed by floors and walls, and then getting converted to long wave radiation as it's released into the space, or the sunlight shortwave being absorbed by the solid surfaces in the building and then conducting through those solid surfaces, warming up the inside surfaces, and then again being released as long wave radiation. So we have both short wave radiation and long wave radiation, but then we also have stratification due to the buoyancy of air, and we have drafts that are created by air coming in contact with different surfaces and changing its density. So we have stratification, we have drafts, we have short wave radiation, we have long wave radiation. We have humidity changes in the building that fluctuates depending on where you are within that space, which is why we call it relative. So as we move towards surfaces that are warmer or colder, then those relative numbers change. We have, people wearing different clothes and doing different activities. So there's lots of things that are going on. And when we look at building codes and only requiring this, it begins to describe why we have so many problems thermally in spaces, is because we don't actually address the dynamics of it. So when we start as designers in practitioners engineering systems, first thing we must do is we must analyze the building itself, the footprint. We have to understand how sun moves across the building surfaces, and that changes how the inside surface areas will also change. And so we need to look at how the geometry of the building fits, how it relates to the sun paths, what are the loads, the heating and the cooling loads in those spaces, depending on the architectural designs and the enclosure design. And we need to make sure that if we're controlling these spaces that we don't, or we try to avoid mixing zones that have extreme loads versus those that have very conservative loads. And so zoning is incredibly important. And we have addressed these in different documents where we look at spaces depending on whether they're spaces for sleeping or working or studying. And what are the temperature values? What could be the typical clothing? What could be the typical MET rates? So if you can, for those that are just in the listening mode, if you could mute your speakers, that would be great. I'm getting some feedback. If it's possible to mute, that would be great. So zoning is important. And then we also need to take a look at building performance. Here in our climate, which is a cold climate, we can categorize our buildings based on their performances. And as you can do in your own climate zones, looking at, you know, buildings that have maybe very poor enclosures, that have maybe large window to wall ratios. Some could be quite high, 80 to 90%. That these buildings have incredibly high loads, high fluxes that we have to deal with, compared to, say, high performance buildings, which have more conservative window to wall ratios, much better enclosures, good architectural design, which includes shading, not only on the structure itself, but across the windows as well. Then these have very low fluxes, and these will drive not only the mechanical systems that we use to condition buildings, but will also influence people's perceptions of the space. So one of the key tools that we have is the thermal comfort design tool. And this tool is available through the Center for the Built Environment, which is a partner of ours through ASHRAE. And they have, for decades now, worked with our Standard 55 committee, SSPC 55, to take the original analog mathematics and digitize it or put it into code so that we can run the analysis online. So you can actually Google this today. You can just Google CBE, Charlie Bravo Echo, CBE thermal comfort tool, and it will take you to the website. And what you're seeing here is a screenshot of that tool. And then what we can do then is put in the values, and it will then predict whether you will be in compliance with ASHRAE Standard 55 or not. And so I'm going to discuss this tool for the rest of the presentation and some other tools that we have available to us to do analysis for building types and mechanical systems using a case study. So the input values that you see here on the left-hand side, these are all addressed within ASHRAE Standard 55. So we have air temperature, we have the mean radiant temperature, again, which is incredibly important for those that maybe didn't take our first and second courses. We talk about roughly 60% of the energy exchanged or energy exchange between the occupant and the space is actually done via radiation, not convection. It's done via radiation, and that is described explicitly in the medical handbooks, also within the ASHRAE handbooks, and also within the indoor environmental design guidebooks. So 60% or so roughly like that is radiation, and it changes depending on ambient conditions and humidity. So we know that as we get into higher temperatures, that the body shifts from the radiant element to more of evaporative and convective. But we should appreciate that radiation plays a big part of it. And this mean radiant temperature describes that experience. And so we can actually calculate the MRT, and I will show you some ways of doing that later on. Airspeed is actually not the airspeed coming out of the registers or the grills, but actually the airspeed across the occupant itself. And we do know that most buildings and HVAC systems, when they're designed properly, normally don't have a concern for high velocities that cause discomfort across the body. In fact, higher velocities, say for example, in the warmer, hotter climates, more humid climates, higher velocities are actually more of a benefit. which is not necessarily the case here in my climate, which is cold, and we don't want to have high velocities because it promotes discomfort. Relative humidity is typically controlled as a specified element. It has a big influence on the body's ability to discharge heat via evaporation. When we get into higher vapor pressures in the room, then the body has less of an ability to discharge heat via evaporation. So we have to make sure that the vapor pressure in the room is lower than that of the skin, so that when we need to cool the body with evaporation, that we can do so. The metabolic rate describes what the person is doing at the specific time, and the clothing value, of course, represents what they're doing or what they're wearing. So these are what we call the general factors and the personal factors described within ASHRAE Standard 55. And when we get the enclosure right and the architecture right, and we have the right interior design and the right mechanical systems, then we can predict with reasonable accuracy how most people will experience the space. And where that is expressed is in the predicted mean vote, or the predicted percentage of people dissatisfied. And the ASHRAE Standard 55 describes that we need to be able to find the right combination of architecture, enclosure design, interior design, and mechanical systems, so that we have less than 10% of the people in the space dissatisfied. So let's look at the input values in a little bit more detail. So let's start with clothing. And this online tool provides an ability to put in, or select, I should say, the clothing value that the occupants might be wearing. And we should understand that within ASHRAE Standard 55, we actually designate what's called the representative occupant. This is a hypothetical person that is in the space that would represent all the other people in the space. If we have multiple representative occupants, then we have to do an assessment for each person. And so an example of that might be, for example, in a healthcare facility where you have patients who might be wearing a different clothing and obviously at a different MET rate than, say, the healthcare professionals themselves. Or say, for example, in a restaurant where you might have service staff, that are working very hard, their metabolic rates are very high, and they might be wearing different clothing than, say, the patrons of the restaurant. So this is an input value. And then as we change that, then we can look at how it affects the compliance. So this slide here shows the PMB and the which is 6%. It's in compliance with ASHRAE Standard 55 based on these input values. And there's this graphical area, the shaded area, that represents the comfort zone. And that dot that's represented there represents the person in the space. So here we have a combination of air temperature, mean radiant temperature, airspeed, relative humidity, MET rate, and clothing, where we are in fact compliant with the space. And so we can put in the clothing values. We can create our own ensembles by just clicking on the tool where it defines choices that we can make, and we can then create our own if we don't want to use the input values. We can also use the predictive tool. So based on ASHRAE research work, we know that when the outdoor air temperature is at a certain value, that people tend to respond to that value by the clothing choices that they make. And so we can also use that tool as well. So that's clothing. Now, as we move into the metabolic rates, again, there's a menu selection there that we look at. We can go in and we can pick, well, so what is this representative occupant going to be doing? Are they working at their desk? Are they walking to and from office equipment? Maybe that they're, lifting the boxes or whatever. So we can actually pick what the person is doing, and then it puts in the metabolic rate. We can then look at the relative humidity or humidity ratio and the other values there, and then we can put those in. And those, again, will be stated values if we're controlling them. If we are actually humidifying a space or dehumidifying a space, then we can put it in there. If it's a free run building where we're actually not doing humidity control, then we have to do an assessment of what the potential, if you will, bookends of the humidity control will be. So what would be the potential high points and what will be the potential low points, and we can do an assessment One of the challenges with this tool is it is very much a snapshot in period of time. It doesn't do a transient analysis. There are other ASHRAE tools that do transient analysis and other engineering tools that do transient. So this one is just specifically a snapshot. So if you want to know what happens at the high end, you have to do a high end assessment. If you want to know what happens at the low end, you have to do a low end assessment. The same is true with the airspeed. And airspeed is something that we've been focusing a lot on within our SSPC 55 committee, which is our standing project committee. And we've looked at it in terms of can we use airspeed, elevated airspeed specifically for improving comfort. And we have now added that a tool in there that allows us to look at elevated airspeed. So we do know that if we find that the architecture results in high mean radiant temperatures and that our mechanical systems can be conservative, allowing air temperatures to rise in the cooling mode, we can compensate for these less than ideal performances by elevating the airspeed. But we also know that airspeed can cause discomfort. And so this is an example, and I'm going to run this simulation or video. I was teaching a course in a room that had a wall mount cassette split unit. And this was in a cold climate. And this person was wearing their winter coat inside our classroom. And the reason was because of the airspeed. So this was, I put my notes on the desk and you can physically see this. So airspeed is important with thermal comfort, but it's also important in terms of distributing whatever is in the air. And so we are now, of course, everybody is quite aware that we're in a pandemic. And so the air velocity in a space not only has impact on thermal comfort, but also on the distribution, of course, of viruses as well. So airspeed is important. And we know that when we can keep it within a certain range, that it will either be unnoticed, people will not perceive it at all, or there'll be degrees of sensation and perception. Some of them are beneficial, some of them need correction. And so these tables exist giving some general descriptions. And so we know that if people are in a high MET rate wearing high clothing and we want to maintain a certain PMV, that we can actually manipulate that airspeed with ceiling fans or desk fans or floor mount fans to bring the space into compliance with ASHRAE standard 55. Now, within standard 55, there's a term we call operative temperature. And operative temperature is the combination of the air temperature and the mean radiant temperature. And so we use a single term to describe the relationships of these two elements. And so we know that when we get the correct operative temperature in a space, that we can then have a higher possibility or probability of being in compliance with the standard, and that when we have a failure to control the operative temperature, which oftentimes has to do with poor architecture, poor fenestration systems, thermal bridging, all of these things will raise the operative temperature, which is due 100% related to the MRT or the mean radiant temperature. So we like to split these values apart. There are times when the MRT equals air temperature. Oftentimes that will be in the interior of spaces, spaces that are not at the top floor, not towards the exterior, but more again, not exposed to the solar loads that we typically find. So we have to do an assessment for exterior zones and those zones that have a high solar load, because they will be directly influenced by the sun, the shortwave radiation, which has an influence on the mean radiant temperature. So very rarely will you see these two numbers exist at the exterior, but you'll see them more similar when we get more towards the interior of the spaces. So we can put those, we can calculate the mean radiant temperature, and we specify what the air temperature is based on our control points. The other thing that we need to pay attention to is what's called the local factors. And the local factors come into play when people have relatively low MET rates, less than 1.3, and clothing values of less than 0.7. So when we have people that are, say, for example, seated at desks wearing, for example, shorts and a t-shirt or sleeveless shirts, then we have to do an assessment on local discomfort. And now we start looking at surface temperatures, which is the radiant asymmetry. So when someone is, say, for example, at a desk, seated, exposed to shortwave radiation from the sun, that the front of their body will experience solar loading, and they might be in a space that's air conditioned. So the back of them might be cool. So whenever you have somebody that has a high surface temperature in front of them and a cool surface temperature behind them, they experience what's called radiant asymmetry. That is the temperature difference, radiant temperature difference between them. And when it gets too extreme, they will complain. Same thing with the floors to walls, or sorry, floor to ceilings. We also know that drafts again, in colder climates can be a problem. So if we know what the airspeed is and what that air temperature is and radiant, that we'll have draft complaints. We also know that certainly, and again, more in colder climates rather than warmer climates, that air temperature coming off a window that is cold will move across the floor, and any ankles that are exposed to these colder temperatures will cause the occupant to sense and perceive a discomfort due to ankle drafts. We know when there's a large stratification between the floor and the ceiling that people will also complain, as well as floor surface temperatures. So if the floors get too warm or too cold, then again, people will complain. So we need to do these assessments, and they can be easily calculated or measured in a space. So floor surface temperature, vertical air temperatures, stratification is all defined within the standard. We know different types of HVAC systems have more or have less stratification, and this is very much tied into the building performance. When we get poor performing buildings and we condition them with air-based systems, that we tend to have higher stratifications. When we have high performance buildings with, say, radiant systems, we have less stratification simply because of the effects of buoyancy on the air. So we can do these assessments and we can see how that affects the occupants. When it comes to radiant asymmetry, the standard defines what are the tolerance or the limitations so that people will sense and again perceive the space as being comfortable as opposed to being uncomfortable based on surface temperature differentials. And here's a really good illustration of radiant asymmetry in a cold climate where we have a glass wall as part of the enclosure, and it is in a cold climate, and they've compensated for the coldness using radiant heating. And so now the surfaces are warm, but we have a cold wall, so we have a temperature differential that people are going to be exposed to. Now this space is a transient space, which means that people are not actually occupying the space. People enter the space and they go from one area to another. And the standard says that if people are not in the space for any more than 15 minutes, that we don't have to do a compliance test. But it's a good way to see radiant asymmetry. And you can also see this in your climates where there is a warm zone where you might have a large glass area exposed to shortwave radiation. And it's quite possible the surface temperature of those glasses easily can get to 40 to 45, maybe even higher temperatures, and that you're air conditioning the space so that you have cool inside surface temperatures and an incredibly warm outside temperature, and that creates radiant asymmetry and discomfort for the occupants. So the drafts we can also see with instruments like thermographic images or Schirlian photography. And so drafts, again, have an impact on the discomfort, and as well as ankle drafts. So all of these things, when we put them basically in the blender, if you will, the analogy that compliance with ASHRAE 55, all of these inputs are like the ingredients of a cake. And when we get all of the ingredients right, the air temperature, the mean radiant temperature, the radiant asymmetry, floors, all of these things, when we get them correct, that we will produce a result that is compliance with ASHRAE standard 55. And that is what we call the predicted mean vote, or the PMV method. And we want to have basically 0 plus or minus 5% predicted mean vote, which corresponds to 10% or less predicted percentage dissatisfied. And when we do that, then we will be in compliance with the standard. So the output value is on the right-hand side, the input value is on the left-hand side. The graph, the psychometric chart, defines the thermal comfort zones, and it's dot that you see there is the actual occupant itself. And you can see with this particular combination, we are in compliance with the standard. So the other tool that was added a few years ago was the solar load or the solar gain on occupants. This was an incredible bump in the performance of this tool because it now recognized how important shortwave radiation was on the occupant. So when we click on this tool, we can see how solar loads impact people's perception of the space. And so we can put in the input values which look at how much of the solar load hits the occupants. So here I am in my office here. You can see that there's some sunlight in the space. My right shoulder here is exposed to the sunlight to my right-hand side. How much of that solar load comes through the window and strikes my right shoulder, and what are the influence of that on my sensation and perception of the thermal comfort? And so that is what the tool added to it. And so when we put in the altitude, the angle, how much of that energy comes through the glass based on the performance of the glass, the transmissivity, if you will, how much of the percentage of my body is exposed to that shortwave radiation, and what is the absorptivity of that surface. So the absorptivity of my skin is different than my clothing based on color and texture. And so we can average that out. And so when we put in these values, then we'll see an equivalent radiant element, or how much does it change the mean radiant temperature perception. So the ASHRAE standard 55 provides guidance if you don't know what the angle at altitude will be in your area. It does provide it. It does provide the absorptivity depending on the clothing and the skin, whether it's a light color or a darker color. And so when we put that into the tool, it does the offset. So you can see here on the slide that the mean radiant temperature delta, that is the difference between the assessment that is done for long wave radiation, there is a delta difference for that, for the short wave radiation. In this case, adds roughly 28 degrees Fahrenheit to the mean radiant temperature. So notice on the background here, we're using, this is the long radiation amount is 77 degrees, left-hand side. If we look at the correction, it is actually 104 degrees. And again, I should have asked in the beginning whether you work with SI or IP, because most of the time we do this presentation for a North American audience. I've done it in IP, so I apologize for that. About 104 degrees Fahrenheit is, of course, very warm, and that then influences the PMV and the PPD. And you can see in this case that when people get exposed to shortwave radiation, all of a sudden our number of people that experience discomfort is incredibly high. Almost 90% of the people would be dissatisfied because of the solar load. So it's an incredibly valuable add-on to the tool, and it's very useful when you're doing design charrettes with architects, because you can say to the architect and the client when they're in the room that due to the choices that you've made, the window to wall ratio, the solar performance, the solar heat gain coefficient, the colors that you've chosen, the thermal bridging, that there's a consequence to that. And that consequence is that most people won't be very comfortable because of your decisions. So let's talk about external shading. Let's talk about reducing the amount of glass area. Let's talk about improving the glazing performance so that we don't have so much of that shortwave radiation coming through. And so that's the solar gain part of it. And then relative humidity, of course, is important, but we also have to put it into perspective, because sometimes controlling the relative humidity has no influence at all. So here we can say, for example, in this condition, with this air temperature and this mean radiant, that even if we bump the relative humidity up to say some 50% to 92%, that we're still we have a problem. We can be in compliance with the standard, but we can't sustain such high humidities, otherwise we'll create mold and moisture problems. So even though we can control humidity to bring the space into compliance, there could be building science issues related to that. So it's not necessarily always good to raise the humidity in the space. Alternatively, we can look at having these conditions where we're not in compliance with the standard due to this relative humidity of 60% and the air temperature, mean radiant temperature. And we could move into compliance by changing the relative humidity from 60 to 35%. But I know you've had Dr. Stephanie Taylor on, who talks about that ideally we want to be between 40 and 60% relative humidity. So even though we could be in compliance with the standard by dropping the relative humidity down, it may not be best in terms of controlling humidity for microbials, for example, and virus transmission. And of course, for respiratory issues that we may want to see it up a little bit higher than that, 40 to 50% relative humidity. So raising the humidity and lowering the humidity may not always be in the best interest of thermal comfort due to other consequences. So that's why we really need to incorporate architectural design, the enclosure design, and air velocity design into our assessments so that we can boost this relative humidity up. Now, the tool has many other features to it. You can actually look at the relationship of relative humidity versus air temperature and see where you can plot that on the isometric or on the psychometric scale. We can look at airspeed versus operative temperature. There's a feature there as well that we can play around with. And then there's also another way to look at multiple scenarios. So we can actually do assessments for 3 different conditions. Again, very useful in a design charrette when you want to look at options. How do we play around with enclosure design, interior design, architectural design, so that we can maybe come up with the best combination so that we're in compliance with the standard. And so we can play around with things like this. So in this case here, what we're doing is we're changing the clothing level. So if you go and you look at the clothing value, the bottom arrow, and you look, we're starting off with 0.71 and 1.2 options. Well, what happens if we provide some flexibility in the clothing and we allow people to drop the clothing level down to 0.69, wear much lighter and less clothing? Well, then that will change how people perceive the space depending on the other conditions. We can look at, metabolic rates and relative humidity and what are the influences on that. And you can see across on the top upper right-hand corner how that changes the predicted mean vote and how we might have compliance in one case and no compliance in 2 other cases. So by being able to play around with that, we can look at compliance and look at the different factors. There's also what's called the natural ventilation method, where we can actually, if the building and the climate is such that it promotes the opening of windows and promotes the use of drafts, ceiling fans, desk fans, these types of things, then as long as that we can be, or that the climate has outdoor conditions that are within the range defined within ASHRAE Standard 55, then we can use the natural ventilation method. The challenges that we have with the natural ventilation method is that as soon as we get into free run buildings, that is that we're no longer controlling them through mechanical means, we're connecting the outside world to the inside world. Well, if the outside world conditions doesn't have noise issues, air quality issues, security issues, then okay, the natural ventilation method works. But if the outdoor air quality is very poor, then when we have open buildings, very quickly, within minutes, literally, that the outdoor conditions become the indoor conditions. So if we don't want to introduce outdoor pollutants, then we shouldn't be using the natural ventilation method. The same thing with sound. If we have buildings that are in areas where the outdoor conditions are incredibly loud, then opening up the windows just introduces that noise into the building. And noise is the #1 biggest complaint today around the world for people and spaces. So from ASHRAE's perspective and the application of the standard, natural ventilated buildings have a lot of benefits in terms of people like the ability to manipulate their own environments. And there's obviously benefits from an energy perspective to be able to connect the outdoor world with the indoor world by opening up the windows and opening up blinds and these types of things, but only if the outdoor conditions promote good indoor quality, as opposed to having us pollute the indoor with too much noise, air pollution, or obviously security issues as well. So we can look at using the tool, whether it's in compliance or not, and that is also very useful. We talked about earlier fan control and speed control. So we do know that when we have conditions like this one, for example, here you can see on the left-hand side, input values, our air temperature is getting high, the mean radiant temperature is getting high. So this is a building that is not very good in its performance. But the airspeed is relatively low, and because of that, we're not in compliance with the standard. But if we provide some local control by increasing the air velocity from 20 to 40, we're doubling it. Now we're in compliance with the standard. So this means that if we can put in ceiling fans or allow people to have desk fans or floor mount fans, then we can find another way to provide comfort in the space by using the elevated air speeds. And so we can play around with these air speeds. And we could do an assessment of that using another tool that's available through the Center for the Built Environment, which is a new tool in the last couple of years, which allows us as application engineers to take a space and we can break it up into areas, and we can locate ceiling fans. Either we can condition the area with one large ceiling fan or multiple ceiling fans, and we can see the consequences of that. And so we can look at what happens to the air velocity that occurs directly below the ceiling fan itself, or as we move further and further away from the fan, what are the consequences? So we know there's an equivalent perception. As we raise the air temperature, it provides convective cooling, which moves, if we're doing evaporative cooling from the body as well, then there's a perception, an offset, a delta, if you will, between what the actual air temperatures are and what the people actually perceive as being comfortable. So it's a very useful tool. And so that's on the airspeed. Now we have mentioned the mean radiant temperature a couple of times, and there's many ways to calculate that. You can get that through a book that's available through LinkedIn, through our website as well. And we describe that process. This link, by the way, this book, by the way, is free. There's no charge for it, where we discuss thermal comfort and the mean radiant temperature calculation, but it's also available through this slide presentation that you're going to get access to. And it's also available through the ASHRAE tools and the CBE tools as well. So lots of ways to calculate the mean radiant temperature. But what we're looking at in the simplest form is a weighted average. There's basically three ways of doing it, the weighted average method. And all we're doing here is we're just taking the area with the temperature, and we can calculate that temperature with a very simple formula that you see there. So it's the air temperature in the space, which is reduced by the U value, which we can calculate, divided by the H, which is a convective coefficient, which is modified by a temperature differential between the air temperature and the outdoor temperature. So if we know what the U value is, which we can calculate based on the architecture, and we know whether the surface is vertical or horizontal, and we know what the outdoor temperature is and what our design temperature is, we can actually calculate that inside surface temperature. So if we know the area, we know the inside surface temperature of each of the surfaces, we can do a weighted calculation, which is shown on the bottom. So this is a very simple formula. It is in the ASHRAE handbooks, chapter 6, HVAC systems and equipment, provides some description for it. Really, the only thing that you need here to calculate this inside surface temperature is the convective coefficient, which is H, and it changes whether you're on a horizontal surface facing up or facing down, or a vertical surface. So if you know what surface you're working with, then you can just put that particular value in and then do the calculation. So it is a weighted average and the very simple formula to do for each of the spaces. So you just take the area times the temperature for each of them, and then put that into your weighted out. In that case, you can set that up in an Excel spreadsheet, and then you can do the calculation. So there we are in this particular space. We've put everything in, and then we've determined that the surface temperature calculation for, let's say, on the right-hand side quadrant of that ceiling, 729 square feet, So roughly whatever that is, 72 square meters times 68 degrees Fahrenheit, which is roughly around 20 degrees, 19 degrees C. And we can do that for each of the surfaces and then come up with the mean radiant temperature. So in this case is about 63.8 degrees Fahrenheit. Now, as soon as we start to add windows, then we have to do an assessment, a weighted assessment for the window area and then the wall area, and then combine the two. So that's what we're doing here. We know the U value of the wall, we know the U value of the window. And once we know that, then we can do a weighted average of the U value, put that into the formula, and then we can calculate the surface, the weighted area of that particular wall with its window, put that in the formula, and then come up with the inside surface temperature. So now this assessment is for a cold climate. So we're down to minus 34 degrees Fahrenheit, which is roughly minus, it's getting close, probably 27, 28 degrees C. For those that have never visited my part of the world, we do get down to minus 40 Celsius, very, very cold, quite opposite to some parts of your country, although your country has cold climates as well. But you can see this is why we get these cold surface temperatures. And so we would do that for that particular surface. And now that has an impact on the MRT for this space. If we have multiple windows, then we have to do an assessment for each of those surfaces and put that in. So the beautiful thing about this is once we can look at the MRT for, say, a building that's been designed and built according to the local codes, then what we can do is we can look at how does that impact our perception of comfort when we improve the enclosure. So I've taken a space, an office space, and we're going to do an assessment for a local discomfort and, a discomfort for a building, for a code building versus one that was designed according to our practice, and Bean is my last name, and that's our specification, versus one that has been designed for net zero energy. And so we're going to do an assessment for that. So we look at the building, each of the surfaces in that office area. We do a calculation for each of the walls, the floor and the ceiling. We look at the weighted MRT for that. We look at then this screen here, the upper left-hand corner, you can see it's for a forced air system. So we're going to condition the office with an air-based system. Then we look at the next option, which is an improved enclosure with using a radiant heating system. And it has obviously a different weighted surface temperature because we've improved the enclosure. And now we're going to compensate for any flaws in that enclosure with a radiant system. So we're going to have a higher MRT. And then we can look at that same office that has been designed for net zero energy using a forced air system. And because we've done major improvements to the enclosure, we can achieve a higher MRT just using an air-based system. So the three conditions that we're going to look at is a building that's been designed according to local codes here in Canada, for example, for this particular slides. So a poor building using a forced air solution. We can look at a better enclosure using a radiant solution, or we can look at a high performance enclosure using a forced air solution. So three options. And then we can use the tool, the thermal comfort tool, to do a PMV assessment. And so we can put all the values in as we've calculated them. And we can see that in the case number one, which is a building designed to code using forced air, that we're not in compliance due to a low MRT, which drives the perception of people's perception of the space. Then you can see how now in case number two, we are in compliance. And the reason for that is that we've improved the enclosure and we've compensated for any flaws in the radiant mean radiant temperature with a radiant system. And so now we have compliance. Or in case number three, we're also in compliance because we've done major improvements to the enclosure and we can then use a forced air system. So again, very powerful because it allows us to look at the combination of architecture, enclosure design, and the type of HVAC system, air-based or radiant-based, and see how that affects the PMV or the PPD and whether we'll be in compliance with the system or not. Now, a number of years ago, ASHRAE developed a tool, 1383, that is available to ASHRAE members. And what we can do is we can use this tool, put in the input values, but the output provides a painted, if you will, color painted 3-dimensional view. And what you're looking at, in this case here, the output screen is people percentage dissatisfied. And so where you have the brighter colors, you can see we have less people comfortable. The PPD is quite high. And as you move further and further away from the glass, the PPD goes down. So the reality in this particular office, in that climate zone, using a code enclosure with forced air, it would not be in compliance. There's very few places in this room, except for the far corner, where someone would actually be comfortable. And that, of course, is not practical. People are going to be sitting in the middle of the room or towards one of the walls in front of their desk. So then we can take a look at an improved enclosure based on the designs that we would use in our practice with a radiant system. And now all of a sudden we have compliance pretty much everywhere in the room is in compliance with the space. And the same thing with something that's designed to net zero energy using a forced air. And so all I've done is I've taken these 3 models, simulations, and plotted them. And so you can present this to the architect and the client, say, okay, if you look at the left side, we're not in compliance with ASHRAE standard 55. The reason for it is we have a high window to wall ratio. We have poor performing glass. We have poor architecture, poor enclosure design, and our choice in our HVAC systems. The combination of that is going to lead to a lot of people complaining about the space, and it's not in compliance with the standard. So what can we do to make it better? Well, we can look at different options in the enclosure. So that's improve the enclosure, reduce the thermal bridging, lower the U values of the wall, put in better glass, and lower the U value of the glass, reduce the amount of glass area, put in a radiant heating system, and then we would be in compliance with the standard. Or we can look at a really high performance enclosure that has very little thermal bridging, and same thing with the glazing systems, and then we can go back to using the air-based system to be in compliance. So that same applies for if you're doing cooling systems. If you take a building, for example, that has, again, poor enclosure, lots of thermal bridging, the mean radiant temperature is going to go up. And if we have lots of glazing, then we're going to have lots of shortwave radiation, poor glazing performance, lots of shortwave radiation coming through. And we could put in an air-based air conditioning system, and we can cool the air system down all we like, but we're not going to be in compliance with the system because the mean radiant temperature is so high. So maybe there's some other things that we can do. We can improve the enclosure, reduce the glass, improve the performance of the glass, maybe look at putting in ceiling fans, and then we can be in compliance with ASHRAE standard 55. So that's the presentation for today. And I really want to emphasize that, you know, as practitioners, that it is our responsibility not just to look at the energy component, that we know that when we understand human physiology and how people sense the environment with their skin, it's a physiological experience, how they perceive it psychologically, what's inside their mind, that our first solutions for compliance with ASHRAE standard 55 is the architecture. That's the number one. Having less window to wall ratios, providing shading on the outside of the building, using lighter colors, orientating the building so that we don't have these large solar loads. That's the first thing. And then looking at enclosure design, reducing the thermal bridging. Do we really need to have the structures that we use to design buildings? Can we do something differently to reduce how much energy gets transmitted from the outside to the inside via conduction? Can we improve the enclosure of the window? And then looking at interior finishes, and that's really important. People oftentimes don't think about interior design, but inside, when we think about, you know, colors, for example, if we want to reflect shortwave radiation, when we should use lighter colors. If we want to absorb shortwave radiation, then we can use darker colors. Interior fabrics, for example, if we want less quality of air because of the breaking down of materials, if you want something to break down, expose it to moisture and shortwave radiation. Well, what happens when you take, for example, fabrics, carpeting, for example, it may be synthetically based, it has hydrocarbons in it. Well, as it breaks down, it turns into gases and particles, and then people, of course, end up breathing that in. So from an air quality perspective and from a thermal comfort perspective, this is important, this interior element. We know that if you have large windows and poor performing windows, that the brightness affects the vision. So we have vision affected. We also have sound, lots of glass, poor glass. We have sound transmission. We have the thermal issues. We have the air quality issues. So all of this integrated comes into play. And so the job of the engineer here is to work with the architect and the client and the interior designers so that we can influence architecture, influence the enclosure design, so that in our mechanical assessments, instead of having large energy intensive cooling systems and energy intensive heating systems, that we can use much more conservative systems, provide good indoor environmental quality with a lot less energy. And so this is really when I started my practice, where we developed our philosophy that when we design for people, good buildings will follow. And there's an intimate relationship between people and the building and the mechanical systems. And I would just encourage you to understand those principles and use the tools available to you so you can design good spaces. So that's my message for today. I'm going to hand the presentation back over to the organizers. And thank you very much for having me on. Yeah, and enjoy the rest of your evening.
We have a question that I think you were mentioning airspeed, and there is a question by Mr. Ronak whether that is the airspeed at the grill level or at the operating level. I think by operating level, they mean the breathing zone.
Yeah, so again, that is actually what the person is experiencing. So the airflow coming across the individual, and it's actually an average, because the airspeed that might be, say, from the shoulders up or the mid part of the body or from the hips down might be different. If it's not, then you just use the single value, but you can, if you know it might be different, then you should use the average between the three.
So that means that some pre-analysis needs to be done to arrive at that figure.
Yeah, so exactly. So in the absence of deliberately putting in ceiling fans, or you're actually deliberately controlling that airspeed, then you should do some kind of an assessment. Now, we do know that when we have high performance buildings, and if we're using standard practice or good practice with our HVAC systems, whether it's displacement ventilation or other types of heating systems, cooling systems, that very rarely will someone experience discomfort due to air velocities unless they're directly underneath or beside the diffuser. So in my office here, for example, the diffuser is actually up behind me on the left. Even when the air conditioning system is running, because of the velocity throw and the spread and the drop of the air, very difficult for me to actually be in a discomfort mode because of where it's located. But if that diffuser was right here beside me on the wall, then it would be blowing right on me. And of course, in that case, it would be a source of discomfort. So in the absence of actually deliberately providing air velocity, location of our diffusers or registers is really important. And our understanding of the throw, the air leaving out into the space, the way it spreads throughout the space, and the way it drops in the space becomes important. And there's guidance on selecting registers and diffusers so that we have the right throw, spread, and drop so that we don't cause discomfort. Now, when we talk about actually putting in ceiling fans or desk fans or wall mount fans to help provide comfort in the space, then we can go back to the CBE tools and look at what the delta difference is by having these higher velocities.
Right. And regarding the CBE tool, you had shared one more tool for doing the advanced analysis of the ceiling fans. Can you share the name of the tool for the audience?
It's the CBE fan assessment tool.
All right.
Yeah, and when you get to the CBE side, the thermal comfort tool, you can just go into the upper menu, and there's a link there, and it'll take you directly to the fan tool. There's also another tool that CBE site offers, which is a mean radiant temperature analysis tool as well. So you can do the MRT there, you can do the fan assessment there, and then you can do a compliance assessment there as well. So it's very useful.
Right, and there's one more last question, which is ASHRAE 55 applicable to patient room and healthcare? And if not, why?
No, that's a really good question. So ASHRAE actually have a standard for healthcare facilities, which is ASHRAE 170. And our committees, our SSPC 170 committee and SSPC 55 committee have worked quite closely over the last number of years. And right now, in the recent publication of 170, it provides guidance for conditions, and it's very clear where standard 55 applies and where it doesn't apply. And I would suggest that you look at ASHRAE 170 first, and then see where can 55 come into play with our assessment. So the ethos, if you will, or the DNA of ASHRAE standard 55 applies to all people in all spaces. We know that this combination will cause discomfort. But in healthcare settings, you're dealing with many, many factors that have to be considered. And this is an example where you have a patient that is lying down, very low met rate. Depending on their condition, they might have blankets over them. They may not have blankets over them. They may be just lying on the bed in clothing or a robe. In these cases, we can use 55 to do an initial analysis of their sensation if they were normally healthy. But that patient might have thyroid issues where their temperature regulation has been compromised. And so they may not experience that space in the same way that a healthy person would experience it. So that's why I would first go to ASHRAE 170, see what ASHRAE 170 says, and then use 55 to provide some further information for your assessment. And so you might be able to say, okay, this particular part of the hospital is for treating people that have conditions that aren't affecting their thermal regulation. Could be orthopedics, for example, right? That, and so their ability to sense the environment thermally is going to be the same as if it was in their home or in an office building. And then you can do an assessment and say, well, based on the architecture in the space and the HVAC system we have here, that this space would be in compliant with 55 or not. But ASHRAE 170 might say, well, no, for this particular type of space, 170 is what we should be using. And I know the question had to do with patients and patient rooms, but 170 looks at things like surgical suites, for example, where surgeons oftentimes want to see temperatures much cooler than what you would see in another space, for example, in a patient room. So first go to 170, then look at 55 and see where the overlap is what my recommendation would be there.
Okay, thank you so much for that information. And just for the benefit of the audience, you mentioned a lot about many tools, and I would just add to that we in India we have the ASHRAE IEQ standard, and this is the first global standard covering all aspects of indoor environmental quality. And the attendees can use the standard in conjunction with the CBE tool to model India-specific conditions. It has all the right formulas that you would need to refer for a thermal comfort analysis, and it can apply to naturally ventilated, mechanically ventilated, and mixed mode buildings as well. So please feel free to go to the ASHRAE website and purchase the standard for your use. So with that, I would like to hand over to the president of the Delhi chapter of ASHRAE, Mr. K.D. Singh, for the concluding remarks and the vote of thanks.
Thank you, Suhas. The vote of thanks is going to be proposed by Dr. Pratima Singh, but
Right.
just to thank Mr. Robert Bean for his enlightening presentation today. I think it was most absorbing, and I've enjoyed every minute of whatever he's presented. And I'm in complete agreement with the way that the approach that he has followed in his past practice, and what he has left a message for all of us, saying that design for people. So I think that's the right message. And also, as we are advancing into times where we're going to see a huge economic growth for a country like India, I think it's important to use tools like this to predict the performance of the HVAC systems as much as we can reduce the power consumptions and energy consumptions and yet not compromise in the indoor comfort and the indoor environment quality. I think that will be the success of an MEP engineer. So thank you, Mr. Robert Bean. We've been privileged and honored to have you on our program today as the Delhi chapter of ASHRAE from all our CWC members, and each of the attendees who's been here. I think all of us go back much richer in terms of our knowledge. And I think when all of us go back, we'll have a lot to think and lot to, work on, and try and incorporate whatever that you've spoken today. So I'll hand this over to Sugdha Tandon, and sorry, to Dr. Pratima Singh. So Dr. Pratima Singh, can I just request you to propose the vote of thanks?
Thank you, sir. And it is my privilege to have been asked to propose a vote of thanks for today's session on using thermal comfort tools to evaluate discomfort probabilities due to enclosure designs and choices in HVAC systems. I, on behalf of Delhi chapter of ASHRAE, IGBC, CII, RC Baroda, Greens, and Rotary, and all our supporting partners, along with the entire organizing committee, and on my own behalf, I extend a very hearty vote of thanks to our keynote speaker, Mr. Robert Bean, director of healthyheating.com and founder of Indoor Climate Consultants Incorporation, for enlightening us all with his knowledge and wisdom in the area of indoor air quality with special reference to thermal comfort. Thank you so much, sir, for briefing us all about importance of art and science of zoning in buildings, keeping in mind the heating gains, interesting facts which you told us about the CBE tools and software for assessing optimal thermal zones and to calculate predictive mean value for ASHRAE standard compliance based on the varied parameters like clothing levels, metabolic rate, or type of activity, relative humidity, to name a few. You also emphasized on local discomfort assessment and calculation of mean radiant temperature. Then you also highlighted on the importance of using shading devices to reduce building heat loads, improving enclosures through windows, and use of different colors, roll of window to wall ratios, etc. Thank you once again, sir, for taking out time from your busy schedule and addressing us with excellent coverage of various tools for calculating thermal discomfort probabilities and addressing our questions and our queries with utmost sincerity and patience. And I also extend my heartfelt thanks to all the attendees for their active participation and patient hearing. Thank you so much, everyone.
Thank you so much. It was my honor and pleasure to be able to share the knowledge that I have. And I hope for continuing health and safety for all of your members, and that you will use this to further the advancement of the science of engineering. So thank you so much, everybody. Thank you.
Thank you.
I think the post-pandemic times, Mr. Robert Bean will be privileged and honored to invite you over to India, and we'll be privileged and honored to have you as our guest. So we look forward to quickly getting over these pandemic times and look forward to seeing you in India. I think more of our members can benefit with the one-to-one interaction that we can have with you. So I think it was a great presentation today. So heartfelt thanks from all of us. Yes.
Thank you again. Yes, it'd be my pleasure. Thank you.
Yeah. Over to you, Suhas. Would you want to?
No, I think we can close the session now. So thank you to all the attendees and the speakers for joining us. On 16th, we have the next session on net zero carbon standards, talking about embodied carbon and operational carbon. So please register. The link is in the chat box and join us again. Thank you.
Yeah.
Bye.
Thank you, sir. Bye-bye. Bye. Thank you very much. Thanks.
Thank you, sir. Thank you very much. Should we close the session, sir?
Yeah, we'll close the session, Tapasji, with the request to all those who are not members of the Delhi chapter of ASHRAE to quickly join in, and we look forward to their being members of the Delhi chapter of ASHRAE. And we promise to bring in a lot of very good programs and value for money. So, and we thank each one of people, all the attendees and the panelists who have found time to be here. So thank you very much. I think we'll close the session now. Thank you,
Okay.
Vineet Charji, the president of the RAS chapter Vadodara, IGBC, CII. I think Dr. Pratima Singh has already done, she's done the honors. So I think once again, I thank you on behalf of the Delhi chapter of ASHRAE, for supporting us. Thank you. I think we can close the session.
Yeah, thank you very much, sir. Thank you. With your permission, I'm going to close the session. Thank you. Thank you, everybody.